Let's talk about equivalent capacitance. The idea is you have some combination of capacitors that you want to replace with a single capacitor. And at the same time, you want the battery to behave the same. You don't want its behavior to change. You want it to be putting out the same current that it was. So that's the idea. And I think the best way to fully appreciate, to fully understand what's going on here with this idea of equivalent capacitance is to essentially derive the formulas, to work through and see how it comes about. So that's what we're going to do. Down here, I've got a circuit. I've got two capacitors connected in series. I know they're connected in series because there's a path between them that doesn't have any junctions. So these are connected in series. I'm going to draw my current. Now, the thing to remember about current, we draw the current in the direction that the positive charges would move. But the protons aren't actually moving through the circuit. It's the electrons that are moving. And the electrons come out of the negative end of the battery. So I have an electron that comes out. It goes over here. It gets deposited on this plate. That's going to make that plate negatively charged. And that electron is going to force another electron off the other plate, thus making that plate positively charged. And that electron that was forced off is going to go over here and get deposited on this plate, making that plate negatively charged. And it's going to force an electron off the other plate all the way back to the battery. And so that remaining plate becomes positively charged. Now, I hope one thing you noticed there is that there was a one-to-one correspondence. In other words, I had one electron leave the battery, and one electron got deposited on this plate, and one electron left this one, and one got deposited on this plate, and one left this plate. And the point is that the number of electrons that end up on this plate is going to be the same as the number that end up on this plate. So these capacitors are going to have an equal charge. So I can already say that, look, Q1 is going to equal Q2. Now let's draw our equivalent circuit. So here's my equivalent circuit. And because I want the battery to behave the same, the electrons are going to leave and they're going to get deposited on this plate. So this plate has to have the same amount of charge as this plate has, and consequently as this one has. If that wasn't true, that would mean the battery was behaving differently. And so we can say that, look, Q1 is equal to Q2, which is going to equal QEQ. So let's just set these all equal to just Q. I'm just going to call them all Q because they're all the same. All right, now let's do our loop rule for each case. So we'll start with our big circuit. We'll start here. I'm going to go clockwise. And if I do that, I'm going to get V0 minus V1 minus V2 equals 0. I know it's minus V1 and minus V2 because I'm going clockwise. Now, notice as I go across the battery, I'm going from negative to positive. That's increasing potential. That's why this is positive V naught. But as I go across the capacitors, I'm going from positive to negative. That's decreasing potential in both cases. That's why these are negative. Okay. We might as well do the loop rule for the equivalent the equivalent circuit here real quick. And so that's just going to be V naught minus VEQ equals 0. Now remember, capacitance is defined to be Q over V, which means V equals Q over C. So if I go down to my equivalent circuit and I substitute that in, I'm going to get V naught. Now, QEQ, remember QEQ, we're just going to be using Q for all these. So this just becomes Q over CEQ. And I can take that now and plug that in here, as well as making similar substitutions in for V1 and V2. Okay. So I'm going to have Q over CEQ, and that's going to equal Q over C1 plus Q over C2. The Q's all cancel, and I'm left with 1 over CEQ equals 1 over C1 plus 1 over C2. And there you go. This, and hopefully you recognize this, but this is essentially our general formula. It's our formula for two capacitors. The general formula looks like this. That's the general formula for capacitors connected in series. In this case, I've got two capacitors, and so I'm going to have, oops, let's see, this is going to be 1 over 13 plus 1 over 2. I'm going to get the common denominator, which is 26. Okay. So I got 1 over CEQ equals, let's see, this is 2 over 26 plus 13 over 26, which is, of course, 15 over 26. This is not the answer. That's it's something I need to make very clear. This 1526 is 1 over CEQ. Now, by the way, you could have gone back to the beginning and plugged 1 over 13 plus 1/2 into your calculator, and you would have got a decimal. But again, that is not the answer. That just equals 1 over CEQ. Okay. So to get the answer, let me write this out clearly. So this is what I have. 1 over CEQ equals 15 over 26. To get the answer, I have to take the reciprocal of both sides. So you're flipping both sides. And 26 divided by 15 is approximately 1.733 farads. And notice that that equivalent capacitance is less than the capacitance of either of the two capacitors I have. That will always be the case for the series situation. Okay, let's look at the parallel case. Okay, so here is the parallel case. And what we've got, well, first off, let me point out that these are connected in parallel, and I know that because a charge comes down, it's going to hit a junction, and it has to pick which path to take. Okay? These are mutually exclusive paths. The charge can only take one or the other. It can't take both. So they're mutually exclusive paths. And that makes the paths parallel, and since there's a capacitor on each path, those capacitors, those two capacitors are connected in parallel. So these two capacitors are connected in parallel, and let's take a look at what's happening with the charge that's coming out of these capacitors. So again, whoops, I've got an electron. In fact, this time I'm going to say I have two electrons. I have two electrons coming down, and they're going to come out the negative end of the battery. They get right here to this junction, okay, and they have to choose. Okay. Well, we'll say one goes this way, and I'll say that one goes this way. Okay. So that means this end is going to become negative, because those electrons are coming down, they'll be here, and the other end becomes positive. Okay. But the important thing, although I picked a nice even number where it was 1 and 1, it doesn't have to be that 1 goes down this way and 1 goes up this way. It could be that 1 goes this way and 5 go this way. Okay. But the key thing is that, okay, the number of electrons, the electrons split. Okay. That's crucial. Why is that crucial? Well, let's look at the equivalent circuit where we replace the capacitors with a single capacitor. So here's my equivalent capacitor. The battery has to remain behave the same. The battery has to behave the same. So let's say I had 6 electrons come out here, they're coming down here, and 1 goes on to C1 and 5 go on to C2. Okay. Well, here I have to have those 6 electrons come out, and all 6 of them have to end up on CEQ. So this gives us a relationship. Q1 plus Q2 has to equal QEQ. That has to be true based on this idea that the battery has to behave the same in both cases, has to put out the same current. Okay, we're going to use that, but before we do, we're going to need to write some loop rules. So let's do our loop rule. I'm going to do a loop rule here for this one. So this is the lower loop. So when I do that, I'm going to get for that lower loop V0 minus V1 has to equal 0. And based on the relationships we already identified, V0 has to equal Q1 over C1. And then I'm going to do the same thing for the outer loop here. So if I do it for the outer loop, I'm going to have V naught minus V2 equals 0, and V naught's going to end up equaling Q2 over C2. And we'll do it down here for the equivalent circuit. And so we're just going to have V naught minus VEQ equals 0. So V naught equals QEQ over CEQ. Okay, for each of these, I want to use this relationship that I have. So I'm going to solve each of these for Q. And that means I'm going to have V naught times C1 equals Q1. I'm going to have C2 times V naught equals Q2. And down here, I'm going to have CEQ times V naught equals QEQ. And so if I take these and I plug them into this formula I've got up here, I get C1 V naught plus C2 V naught equals CEQ V naught. The V naughts all cancel, and I get C1 plus C2 equals CEQ. And you might already know that the general formula for capacitors connected in parallel. And so what we see, a couple things we see here, is first that the capacitors behave the exact opposite as the resistors with regards to this idea of equivalence. In this particular case, I would just go ahead and say, all right, C1 is 13, C2 is 2, and so my equivalent capacitance is just 15 farads.